In section 5.2, we're going to discuss logarithmic functions and their graphs. To begin, let's define a logarithmic function. For x greater than 0, b greater than 0, and b not equal to 1, first of all, notice that these conditions here, by the way, are the same kind of conditions we had when we defined an exponential function. For positive values of x, we say that y is equal to, this notation is read log base b of x, is equivalent to saying that b to the y equals x. What the logarithm is equal to is it's equal to a value, let's call it y. It's the value, or the exponent y, that you would need to raise the base b to in order to get the value x. So whenever we write out a logarithm, you can always kind of think of it as equivalent to some kind of exponential statement. Whenever we have the exponential statement like this, there's three key pieces. We have the base, we have the exponent that we're raising the base to, and then we get the resulting value from that computation. Very similarly, whenever we write out log base b of x equals to y, we have the same key pieces but arranged slightly differently. B is the base, x is the value, and what the logarithm is equal to, what we're looking for is what exponent do we need to raise the base to in order to get the value x. Okay, so again, when you see a logarithmic statement, there should be three key pieces that are attached to it. The subscript of the log is the base, the quantity on the inside of the logarithm is the value, and what this is equal to is the exponent that you would need to raise the base b to in order to get that value x. We can now think of this at the level of a function. We're going to define the function f of x equals log base b of x is referred to as the logarithmic function with base b. Okay. Whether you say y equals log base b of x or b to the y equals to x, these are two different ways of expressing the same thing. We will refer to this as being in exponential form, and we will refer to this one as being in logarithmic form. Let's take a look at example 1. We are simply asked to write each equation in its equivalent exponential form. Okay. So if we're going to do that, again, we're going to have the same three key pieces. We need our base to the exponent should give us some value. So if I go ahead and I look over here, here's our log statement. Remember, this bottom number is the base. The x, the thing on the inside, is the value, and what the log is equal to is the exponent. Okay. So the equivalent exponential statement would be 7 to the third power equals x. We don't have to compute this. We're not asked to solve for x quite yet. We're just asked to rewrite it as an equivalent exponential form, and this is what it would look like. Let's come over here. Let's do the same thing, starting by writing the base. The base is right here. That's b. The exponent is the thing that the log is equal to. That's the 2. So b to the second power equals, and the value that we get is the thing inside of the logarithm, which is 25. So we get b squared equals 25. Let's do one more. Start by discovering the base. That's the subscript of your log, so the base is 4. The thing that the log is equal to, the y, that's the exponent, and the value is the thing inside of the log. So we would get 4 to the y equals 26. Let's now do the same thing, and let's write each exponential equation in logarithmic form. Again, the way that this is going to look, there's three key pieces. It's always the log of the base, the value is on the inside, and the exponent is on the other side of the equal sign. So let's begin by identifying the base. This is base 12, so it's going to be log base 12. The value is the thing on the other side of the equation, so log base 12 of x equals the exponent, which in this case is 2. So when we say 12 squared equals to x, this is equivalent to saying log base 12 of x equals to 2. Let's do another one. We want to start out by writing the log of the base. Here, in this case, the base is the variable b. What goes inside is the value. That's the number 8. And a logarithm is equal to an exponent. In this case, the exponent is 3. B cubed equals to 8 would be equivalent to saying log base b of 8 equals 3. Let's come over here and look at the last one. The base is e, so we would say log base e. The value is 9, and log is equal to an exponent. In this case, the exponent is y. So we are going to say log base e of 9 equals to y. This particular log, we're going to see it in the notes in just a minute, but log base e is a special base because e is the natural number. A lot of times we will see this written in shorthand notation as simply ln. So in your calculator, you'll even see this as a button. There's no log base e button on your calculator, but what you will see is there's an ln button, which stands for log base e. Remember that logarithms are exponents, and they make it possible to evaluate some logs by inspection. So some of these values we can actually work out by hand. For example, if we wanted to find log base 2 of 32. Log base 2 of 32, if we think about what this is, so if you were asked to compute this, let me just call it an unknown. Let me call it a question mark. Okay. If we convert this to the equivalent exponential statement, what this would be is we're asking 2 to what power gives us the value 32. And if we think about our multiplication tables or just simply multiplying, it would take 5 2's multiplied together. 2 times 2 times 2 times 2 times 2 would be equal to 32. And because of that, what we would say is that log base 2 of 32 would be equal to 5. Let's go ahead and evaluate all of these ones. In example 3, let's start with log base 2 of 16. If you're not sure what the value is, a common technique you can do is just set it equal to x. So log base 2 of 16, if I don't know what it's equal to, let's just go ahead and call it x. The technique that's oftentimes useful is now we're going to go ahead and let's rewrite this as an equivalent exponential statement. The base is 2, the exponent is x, and the value is 16. And now from here, we're just trying to ask the question, 2 to what power would give us 16? And the answer is it's going to be 2 to the 4th. If you do 2 times 2 times 2 times 2 times 2, that's going to be equal to 16. So we found that log base 2 of 16 is going to be equal to 4 because 2 to the 4th gives us the value 16. Let's do the same thing with part B. We want to find log base 7 of 1 over 49. This is equivalent to saying that 7 to the x equals 1 over 49. So we're looking for what exponent would we have to raise 7 to in order to get 1 over 49. Well, one thing that we know is that 7 squared is 49, right? 7 times 7 is 49. But in order to get a 1 over, to get that reciprocal, we know that that would have to correspond to a negative exponent. Therefore, the value should be -2. Just a quick check if we wanted to. If I take 7 and raise it to the negative second power, that's the same thing as 1 over 7 to the positive second. And that's going to be 1 over 7 times 7, which is 1 over 49. So log base 7 of 1 over 49 is equal to -2. Let's take a look at the last one. We want log base 2 of the 5th root of 2. And if you don't know what it is, let's just simply go ahead and call it x. We can now take our logarithmic statement and rewrite it as an equivalent exponential statement. This is saying that the base 2 to the exponent x should be equal to the value, which is the fifth root of 2. So we want to solve this equation, and one of the things that we quickly realize is that on either side of the equation we have the value 2, which we can think of as a base. So we have 2 to the x on the left-hand side, and we recall that if we have a fifth root, every radical can be rewritten as a rational exponent. The fifth root is equivalent to the 1/5 power. And now we can use the properties of exponential functions. The fact that an exponential function is 1 to 1 implies that if you have an equality where the two bases are equal to each other, the only way that that can happen is if the exponents are also equal to each other. So we get that the exponent here, x, must be equal to 1/5. So log base 2 of the fifth root of 2 is equal to 1/5. And again, just from what we know about radicals and exponents, this should make sense. If you take the base of 2, and if you raise it to the 1/5 power, 2 to the 1/5 power, we know is equivalent to the fifth root of 2, which is the value that we were looking for. Some common basic properties of logarithms. Log base b of b is equal to 1 because 1 is the exponent to which b must be raised to obtain itself. So if you think about the way logarithms work, log base b of b is the exponent. It's the exponent that we would need to raise this base to in order to get this value. Well, this value, if you think of b, it's the same thing as b to the first. So we need that exponent of 1, and that's why log base b of b equals to 1. It's also the case that log base b of 1 will be equal to 0. And the reason why that's the case is if you try to think about this, what could possibly be the value of log base b of 1? Well, the base to the exponent would be giving us the value. And one of the things that we recall is that any non-zero base to the 0 power equals to 1, right? Anything other than 0 to the 0 power gives us the value 1, and therefore log base b of 1 equals to 0. So these are two basic properties of logarithms that we want to eventually put to memory. From what we just talked about a moment ago, we can now evaluate example 4. Log base 7 of 7, that's simply going to be equal to 1 because 7 to the first power gives us 7. And for part B, log base 5 of 1, log of any base of the value 1 will always produce an exponent of 0. So log base 5 of 1 equals 0. One of the things that's nice about logarithms is they actually finally give us now an inverse to our exponential functions. If you have the function f of x would be equal to b to the x. It's a 1-to-1 function. If you were to graph it, it passes the horizontal line test. Therefore, it's going to have an inverse. The inverse function of the exponential function b to the x is the logarithmic function with base b. Okay. And we can check this. If you remember, what was the condition or the property that inverse functions had to satisfy? Well, the answer is if you did the compositions of the two functions in any order, we should get out the value x. So if you look at these two statements here, these are simply a matter of composing these two functions and showing that they're inverses of each other. So log base b of x, let's look at the first one here. Log base b of b to the x. This is asking what exponent would we need to raise the base b to in order to get the value b to the x? Well, we can see it's sitting right there. We need to raise b to the x power in order to get b to the x. So log base b of b to the x equals to x. Let's look at the second condition. Here we're taking b and we're raising it to a logarithm, which is ultimately just an exponent. Log base b of x, that's the exponent that you would need to raise the base b to in order to get the value x. But then what we're doing is we're actually taking b and raising it to that exponent. Therefore, the value we would get would be the value x. Okay. So this kind of highlights and illustrates the properties that b to the x and log base b to the x are inverses of each other. Again, it's good to mentally kind of go through and understand, based upon the notation and what things mean, why that composition gives us x in each case. Mechanically, what I will see that some students will do, and they'll just kind of put it to memory, mechanically it works, even though philosophically it loses a lot of the meaning, is that if students understand that log base b and b to the x are inverses, then what a lot of students will do mechanically if they're working through a problem or solving something is they'll just cancel log base b with the base of the exponential and get x, cancel the exponent, cancel the log part, and they just get the value part here. Mechanically it works, but just please make sure you understand exactly why these two are inverses of each other. Let's take a look at the next one. In example 5, we want to evaluate these two expressions. Log base 4 of the value 4 to the 5th. This is the exponent that we would need to raise 4 to in order to get the value 4 to the 5th. That's simply going to be the exponent of 5. For part B, we're taking 6 and raising it to the log base 6 of 9 power. Again, if you want to think of it a couple different ways, log base 6 of 9 is the exponent that you would need to raise 6 to in order to get the value 9. And then we simply take 6 and raise it to that exponent, so that will produce the value 9. Alternatively, again, if you want to kind of think of it like I described a moment ago, for those students who like to think of log base 4 and the exponential part canceling, this will produce the answer of 5. The exponential part 6 with log base 6, and again, ends up canceling, producing the answer 9. Much like in the way we saw that there was two classes of exponential functions based upon whether the base was bigger than 1 or if the base was between 0 and 1, we also get two classes of logarithmic graphs. Once again, those whose bases are bigger than 1 and those whose bases are between 0 and 1. If you take an exponential function, our type 1 exponential function, where the base was bigger than 1, we knew that the graph of that exponential function looked like this. If we recall, one of the key properties we discussed as the relationship between the graph of a function and the graph of its inverse is that they were symmetric with respect to the line y equals to x. If I take our known exponential function and I reflect it about the line y equals to x, we would get this graph right here. We know the inverse of the exponential function b to the x is going to be log base b to the x. So this graph that's in reddish or maroon, this is the graph of log base b of x for a base bigger than 1. There's a couple key features we want to memorize about this graph. First of all, its domain is the set of x's from 0 to infinity. You can't ever plug 0 inside of a log. Furthermore, that logarithmic function will actually have a vertical asymptote at x equals to 0. It has a x-intercept of 1, 0. So that's always a very important point you want to mark on your logarithmic functions. We want to always mention where it crosses the x-axis. And then other than that, it will rise very slowly towards positive infinity. So it'll go up and up and up, but it rises awfully slowly. On the other hand, if we recall the graph of b to the x, when the base was between 0 and 1, that exponential graph looks something like this. If we again take it and reflect it about the line y equals to x, we would get a shape that looks like this, which would be our graph of log base b of x for b between 0 and 1. Some of the common key features that we also see again is that it has a vertical asymptote at x equals to 0, like this. It has, once again, a x-intercept of 1, 0, so that's consistent. The difference, though, between the other type of log graph is that for bases bigger than 1, the log approached negative infinity as x approached 0 from the right. If the base is between 0 and 1, then as we approach 0 from the right, that graph of that log will actually approach positive infinity. If we go to the right, it's going to go down. It needs to pass through the x-intercept, and then it will actually approach negative infinity slowly. So we now have two brand new graphs that we want to add to our parent function list. Please make sure you memorize what the graph of log base b of x looks like, depending upon if the base is bigger than 1, or if the base is between 0 and 1. Again, common key features that are shared by both of them. Make sure you always list the equation of the asymptote. It's x equals to 0, and we also want to plot the x-intercept, which is the order pair 1, 0. In the notes, there's this chart here. We pretty much summarized it. The domain is from 0 to infinity, where the 0 is not included. The range will be all real numbers. These graphs, in either case, go all the way down and all the way up towards negative infinity and positive infinity. So the range is all real numbers. We talked about the x-intercept, and then we talked about the direction that the graph opens. We can now discuss more in-depth logarithmic functions. If we have more than just a simple x on the inside, the domain of any logarithmic function is going to be the set of values for which the inside of it is greater than 0. So if you're going to take the log of a value and you want to get a real number, it must be the case that the thing inside of the log must be strictly greater than 0. Okay? So if you ever have a log expression and you want to find its domain, simply put, you just take whatever's on the inside of it, set it greater than or equal to 0, solve for x, and that will produce the domain of your log function. When working with logs, it turns out that we don't really need to use a log of every single base if we just know the values for one special log. And in general, there's two special logs that commonly get used. The first one is log base 10, simply because our number system is base 10. So if we have log base 10 of x, usually we will use the shorthand log of x. This is referred to and called the common log. When you look at this notation originally, it looks like it's kind of incomplete. A lot of people will look at it and say, well, wait a minute. Anytime we have a logarithm, we're supposed to have a base number here. If you don't see a base number, it's not a mistake. This is what's called common log, and it's understood that that is going to be log base 10. Okay, so just log by itself with the base missing is log base 10. Some of the common properties of log base 10 is, once again, log base 10 of 1 is going to be equal to 0 because 10 to the 0 power gives us the value 1. Log base 10 of 10 is 1. And then properties 3 and 4 here just show the inverse nature between the exponential function 10 to the x and its inverse, which would be log base 10, or what we'll call common log of x. The other popular logarithmic function that gets used, we talked about earlier, is what's called the natural logarithmic function. The function with the natural base e, remember e is that value, it's approximately 2.71828 blah blah blah. Much like pi or the square root of 2, it's an irrational number that never stops in its decimal expansion, nor does it ever repeat itself. As a shorthand, instead of writing log base e of x, we write it as ln of x. Okay, so whenever you see this notation ln of x, it's the special logarithm whose base is e. Highlighting some of the same properties we saw earlier, the ln of 1 is 0 because e to the 0 power gives us 1. The ln of e, the exponent you would need to raise e to in order to get e to the first is 1. And then properties 3 and 4 show the inverse nature between the exponential function e to the x and the logarithmic function with base e, which is ln of x. Let's take a look at example 6. We want to get some practice evaluating some of these. In example A, let's find log of 100. And if you struggle and if you don't know what it is, go ahead and convert it to an exponential statement. Let's say that log of 100 equals to x. And if it helps, we can decisively write in the base here. So log of 100 means log base 10 of 100 equals to x. We can now rewrite it as an exponential statement. The base to the exponent equals the value. And then just from basic multiplication tables, we know 10 times 10, or 10 squared equals to 100. Therefore, log of 100 equals to 2. The ln of e, this was one of the properties we saw earlier, but the ln of e is equal to 1. The reason for that, again, if you're having a hard time with it, think of it like this. Ln is really just nothing more than log base e of e, call it x. This is asking the question, e to the exponent of x needs to give us the value e. Well, e by itself is just e to the first. And again, if the bases are equal, then the exponents must be equal. So we see that ln of e is equal to 1. Log of 1 over 1,000. Well, we know that 10 to the third power is 1,000. But to get a 1 over 1,000, we need a negative exponent. So log of 1 over 1,000 should be negative 3. Again, if you can't see that, or if you're struggling with it, you can just use the same trick we did earlier. Write it explicitly. Common log is the same thing as log base 10. We have 1 over 1,000. Call it x. The base to the exponent equals the value. And then from here, just kind of known facts. 10 to the third gives us 1,000. To get the 1 over the reciprocal, that requires a negative exponent. And that's why it's going to be negative 3. The ln of 1, we know that that's equal to 0. This is asking the question, e to what power gives us 1? Well, we know that anything to the 0 power is 1. So that exponent, that value is going to be 0. In E and F, where we have some inverse properties coming here, 10 raised to the log base 10 of 700. Again, the exponential function with base 10 and the common log with base 10 as well are inverses. So if you think of them as canceling out, this will produce just the value 700. And in part F, we have the ln of e to the sixth. Log base e and the exponential function e are inverses. So those will cancel each other out, and we get just the value of 6.